Okay, welcome to our fourth presentation this afternoon at our annual Thesis conference. We want to welcome family and friends, campus members, and especially our expert discussants sitting in the first row. You'll have a chance to ask questions both in the public session and privately with the team after the public session. All our teams, all our senior teams have been working hard for 3 years, so we're very eager to hear what they've come up with. So without further ado, let me introduce Team Cogen.
Thank you, Dr. Wallace. Hello, everyone. We are Team Cogen University Technology, or also known as Team Cogen. My name is Christopher DeCaro. This is Dylan Rabois, Christine He, Jeff Sang, Kenny Boschel, Ethan Shaler, Michelle Parks, and Colin Kennedy. And our team mentor is Charlie Carr. So thank you all very much, and let's get started. So our research statement is basically, to what extent can university campuses, such as the University of Maryland, significantly decrease their carbon emissions through what's called combined heat and power? Combined heat and power is a form of energy production that produces both electrical and thermal energy. So let's go into a little specifics about what CHP actually is. CHP begins with what's called a gas turbine. This gas turbine takes in natural gas, and as a result of combustion, produces electricity. This electricity is used in the campus right now with these lights you have going on right now. Now, after this combustion occurs, there's a lot of thermal energy, a lot of high temperature heat. And this temperature heat is then captured in what's called a Hertzig, or a heat recovery steam generator, which is over here on the right. This Hertzig basically takes that high temperature thermal heat and turns it into high pressure steam. This high pressure steam is then piped through what's called a steam turbine, producing even more electricity. Now, after the high pressure steam goes through the system, you then have what's called low pressure steam, which is the remnants of the high pressure steam being produced electricity. This low pressure steam is then piped through the campus through what's called a district heating system, and basically used to heat this room we have right now. So basically you're trying to maximize the amount of energy you're getting out for the amount of input you're putting in. I'm going to hand it right over to Ethan, who's going to talk a little bit more about what our research specifically entails.
So, as was mentioned previously by Chris, our big question is, how can CHP be used to reduce the carbon emissions on a university campus? And that's a very sort of nebulous question and has a lot of potential ways of being answered. And given the interdisciplinary nature of our team, we saw 3 different perspectives and 3 different ways of solving this problem, if you will. And those were an engineering perspective, a business perspective, and a policy perspective. And by combining the information that these 3 teams we had on our team doing research, we were able to basically develop a comprehensive and interdisciplinary method of solving this rather complex problem. So, before we jump into all the research and the results, we did want to address one concern that's been raised a lot during the process of this project. And that is, why are we not doing something that's sort of this quote-unquote green energy, which has gotten a lot of buzz in the past few years, can sort of run the gamut from wind or steam, solar energy to some sort of steam produced through geothermal processes, or even nuclear energy is thrown around as sort of a green energy solution. And they're all great long-term solutions to creating sort of this carbon neutral energy source on campuses, but in the present they're not practical for a lot of different reasons. And one of them is presented here in this graph, which shows the total overnight cost, which is basically, if we wanted to build a system that produced a certain amount of energy tomorrow, how much would it cost us? And as you can see, conventional fossil fuel sources are by and large a bit cheaper, and sometimes substantially cheaper in the case of CC, which is a combined cycle, that's a gas turbine. And advanced CC, also advanced combined cycle gas turbines, so very efficient turbines running on natural gas. And they're perhaps one of the lowest carbon emitting forms of conventional fossil fuel based energy production. So they're a very nice system in terms of intermediary process between sort of the conventional coal-fired power plant and some of the more expensive but obviously less carbon-producing systems like solar power. And from a university or campus perspective, this upfront cost, how much is it going to cost to build the system, is a major concern for them. So as a result, what we're seeking to do is find sort of this incremental step in the process of creating a really good, very low-emitting system that runs on fossil fuels, and have that as a great intermediary for some of the future plans we have. And just a note about these future plans, the university is a member of the President's Climate Commitment, and that's actually a consortium of about 670 universities around the country who have all developed action plans to get to a carbon neutral state. And our target for that is 2050. So obviously, a project like ours, which is reducing substantially our carbon emissions in a short term, while still having natural gas, is a great intermediate step. So to jump right into the research. From an engineering perspective, we sought to improve the efficiency of a CHP system. And to start with that, we had to know, well, how efficient are conventional CHP systems around the country? So we have University of Maryland as a great example, and we were able to learn how a CHP system really runs, what are kind of the parameters for pressure and temperature throughout it. But we had to look more broadly. And to get granular data that we really couldn't find in any previous publication, we had to create surveys. So we basically surveyed 51 universities around the country that have CHP systems, and we're basically trying to identify how efficiently do they run. And the chart over there demonstrates how 8 of them run. The red actually indicates the University of Maryland. And the comparison is the blue represents basically turbine efficiency. So if it was just running a turbine, how efficiently is it producing electricity? And the green represents actually how it runs as a whole CHP system. And as you can see, it's a substantially higher efficiency, up in the 60, 70, 80% range. So we know that they're working well, but you can also see a wide variation in the efficiencies. And so that obviously means there's room for improvement. And as a final note, we would like to show that we only had 11 out of 51 full responses in terms of data we could use. And the reasons for that are numerous, but they all revolve around different types of low-quality data or non-responses. And Colin's going to explain a little bit more what we mean by that.
So one of the major hurdles that we faced in addressing this question of how the current university CHP campuses are operating their power plants is very poor data responses. And one of the major hurdles to this was a general sense of apathy in the community of people who run these CHP plants. As mentioned earlier, we only have 11 out of 51 responses, which, as we talked to various people around the country at conferences, is a fairly typical response rate for a survey like this because of this general sense of apathy in the community. Now, in a more technical sense, there are other hurdles that we came across to gathering this data. Some of them are, there are many, but more important ones are that in order to calculate the efficiency of a gas turbine, you need to know certain properties of the air that's running through the turbine. And some of the major ones that the people who are running these plants are not able to even measure or record on their operation parameters are the air properties after combustion in the turbine and the amount of air that is flowing through the turbine. The graph on the right is actually, we went to our plant here at Maryland and measured, because we were running simulations of the program of the CHP plant here at Maryland. And we found that the airflow rate through the turbine is actually about half of what, on the control screen, is actually about half of what they should have been running. So we went to the University of Maryland power plant and we took physical data on the air moving through the turbine. And the raw data is shown on the right. Dylan, can you click on that? And this, with a little bit of math, we were able to get a fluid flow, or a air velocity versus position in the stack. And from that, we were able to determine that the air going through the turbine is actually the rate that it should be from the spec. It's just that the measurement system on these turbines is a factor of 2, 100% off. So this was a major hurdle in determining the efficiencies of all these systems. And it just shows there's room for substantial improvement. So with that in mind, we're looking for what kind of improvements can we make theoretically to a very small, less than 10 megawatt plant. Now, a lot of research is out there on very large gas turbines. We're talking hundreds of megawatts. But very little research has been done on very small turbines like we would use here at the University of Maryland. The plot here is we're trying to answer this question of, well, how is a smart way to use all these improvements that are being used in larger turbines. The plot here is actually a plot of a cycle enhancement called regeneration. And what we show here is that it is actually beneficial for a small university